All right, 6-3, day 2. We're still diving into binomials. But at this point, I like showing you these two formulas because, in day 1, when we introduced binomials, I mentioned that you can think of them like a distribution, right? Kind of like a normal distribution. Which kind of leads to, hey, wait a minute here. If it's a distribution, shouldn't it have a mean and standard deviation? And it does, right? And there's the formulas for them. Be sure to pay attention to this note here. These are in your formula packet, and they are only to be used with binomial distributions. They don't apply to any other situation, okay? The only other thing that gets really interesting with these, I'm going to get to it eventually, if n times p, which if you really, n times p would be like the number of successes, and n times 1 minus p is the number of failures. When there's at least 10 of those, something really interesting happens. You don't need to know what it is yet. The book has it if you come across it. I'm going to show you eventually, just not yet. But there's your mean and standard deviation. Super easy formulas to use because remember, if you're using a binomial, n and p. N is the number of trials, p is the probability of success. Before we even state that we're going to use a binomial, we have to be clear that we know what those two numbers are. All right, a lot going on down here. So it's a taste test, okay, for a regular and a diet soda. And so the paragraph is just kind of describing that it's a little well-designed experiment that they're doing. They get both in random order, and then we're trying to see if, of the 30 participants, if they can identify which they had, the regular and the diet. So the first part here, just to explain why this setting would fit a binomial. Okay, and I talked in day 1 that you're only going to dive into this if you're asked to. Right? Typically, bins is a mental process. Like you want to go through that to make sure that, okay, I'm going to use a binomial distribution for this problem. That's just your little safety net to make sure that you can. Here, though, it's specifically asking. So here you would write it out. So I've got 4 parts. The first one on the top left there, guess right or guess wrong, that's binary. That's what they could. That every single volunteer in our little test could respond in one of those 2 ways. They were right or wrong. Independence, one volunteer's guess should not affect another. And then N and S, right? We said there you should just identify the numbers. N is 30, P is 0.5. Okay? N is 30, P is 0.5. Now this number can be a little bit tricky to see. That's coming from this. We're kind of trying to gauge the odds that they're guessing, because 23 out of 30 guessed right, which seems high, but maybe they just got lucky. Maybe they're guessing in a lot. Maybe they really can't taste the difference and they're just guessing right. So for this problem, I'm going to assume that everybody's guessing and kind of go from there. Okay? So using our formulas, here's our mean. This is a good one to see first because if you kind of think about this number, it makes sense, right? There's a 50-50 chance if you're guessing you'll get it right, and 30 people were involved in the process. So on average, we'd expect that 15 of the 30 should guess correctly, right? Some should get lucky and get it, and others may not, and they're guessing wrong. Now, if they are guessing, the number of correct guesses is going to vary. So yeah, the square root of n times p times 1 minus p, which is still just also a half. Okay? And you get about 2.74. All right, so if our volunteers are guessing, so on average it should be around 15, but we'd expect that to vary by about 2.7 guesses if this experiment was done repeatedly. Okay, now remember, we were up at 23. We were up at 23. Okay, now on this last part here, does the fact that 23 out of 30 give convincing evidence that the volunteers can taste the difference? Okay? This problem, you don't need to write this out in your response. This is just for your notes. It's a binomial CDF that is going to help me take a look. Okay? I want to figure out the probability that if they're guessing that at least 23 would guess right. Because the way I've set up this binomial problem, and it's easy to lose sight of it, but again, we're assuming that they're guessing. Okay? That may not be the case, but that's the assumption that we've made. Okay? I have a greater than, that has to get switched to a less than. That probability that 22 or fewer volunteers would guess correctly, I can get that from binomial CDF. Okay, so when I'd go in there, I'd say, all right, n is 30, p is 1 out of 2, x is 22. That's all I need to tell the calculator. It'll do the rest. And we get 0.9974. That is what the calculator would tell you directly. I subtract that from 1, and I get 0.0026. That is the probability that if our volunteers are guessing, that 23 or more would guess correctly. Okay? That seems pretty low. All right, the odds that they're going to have that many guess right, pretty unlikely. So the better explanation is that our volunteers can actually taste the difference. Okay, and that's what you can see in that interpretation underneath. I would say that there's probably a difference in taste between the regular and the diet. Okay, they're just that, or our volunteers are getting extraordinarily lucky in their ability to guess which one they had. All right, so I'm headed back to our quiz, our guessing quiz. All right, now I know we established this before, but I just want to start to be clear. If you were doing this like a test question or a homework or a quiz question, what am I looking for as far as a response? Okay, right off the bat, I would say x follows a binomial distribution with n equal to 10 and p is 1 out of 5. If you have that on your paper, you are pretty much good to go with the calculator. That's really it. Okay? Consider that sentence like your work. Okay? That's like your work. All right, for the mean, two. So if I want an interpretation there, I'd say on average, we'd expect back up here. On average, if students are guessing, which they are, I mean, that part I could actually probably leave off, because the context, this problem made it really clear. They have no choice, right? There's just a randomly selected correct answer. There's no questions. Students are just going through and guessing. If they're guessing, we'd expect them to answer 2 questions correctly. Now, from quiz to quiz, that number is going to vary. Sigma is 1.27. So again, I'd say on average. We would expect the number of correct guesses, or I could just say correct answers, to vary by 1.27 from the mean. Okay, so we'd expect on average about 2 correct guesses, and we'd expect that to vary by about a little over a guess, right? So just think about it in terms of just kind of common sense. Obviously, 2 guesses is not going to be a surprising outcome. That's what we would expect to happen. 1 correct guess, 1 to 3, that wouldn't be that crazy. All of them wrong, up to 4. 5 would be getting a little high, but any score that's like 5 or above is going to be, probably not that common. And in fact, in this question, we'll see just how uncommon that would be. All right, so there's the mean. What's the probability Patty's score is more than 2 standard deviations above the mean? Well, standard deviation is 1.27. 2 standard deviations above the mean is 4.54. So this is actually asking us pretty much just that. What's the probability Patty will get at least a 5? One minus the probability that she gets a 4 or less. Okay. Right, this is another. It's good to have these marked in your notes. This is a CDF question, and you would have to say that n is 10, p is 0.2, and that x is 4, and we need to take the complement of that. So that part I put over here on the side, the CDF and all this stuff, okay, for this problem you would not need to write that out. Right, up at the beginning I already established that this is a binomial and that n is 10 and p is 0.2. That's just a reminder for your notes that that's what we did. Oh, there's a lot of stuff down here. This kind of gives you a situation as to why this is the case. I don't want to get into that. It's there for you to read if you want. This is your first look at what we call the 10% condition. We'll get into it much more later, but I just wanted you to see it for the first time now. But basically what it says is if you're sampling, don't take more than 10% of your population. You always want to stay under that. Okay, that might be kind of a weird thing, like you're thinking that there's such thing as samples that are too big. And some of the formulas that we have seen don't exactly work if we sample too big. And what it's showing you down below is the whole thing about replacement. We've talked about that, replacement and without replacement. If we're sampling without replacement, but we stay within the 10% condition, it doesn't really matter if, you know, the probability of a random selection is changing as someone is removed. Okay, that's what it's showing you the numbers of a case where there's some sampling going on, but you're staying within the 10% condition, and it shows you that if you do that, whether you sample with replacement or without, the numbers basically don't change at all, and you can kind of always assume independence. This gives you the outline for a geometric setting. Here's the deal. I don't necessarily want you to think about it like anything, like it's a different type of situation. You don't really have to be aware of a geometric to do that. Okay, it has a formula and a calculator feature, which I'm not going to show you because you really don't need to know it. The bits thing, again, it's there if you want it, but the bottom line is you're looking at one of these types of problems. When it says a particular outcome, we tend to word it as first success. That's where it's very different from a binomial, as it's not going to specify the number of trials, because you're looking at like when a first success is going to happen. Okay, but I don't get into all the calculator stuff, and I don't get into bits, because as far as showing work, you really don't need to. You can solve these with just rules of probability. Okay. So here's the setting. Okay, it's in Monopoly, rolling doubles, right? To get out of jail. And it's familiar context for us. We've already looked a little bit at the probability of rolling doubles and whatnot. This problem is asking us the probability that it will take 3 turns to roll doubles. Now, if I just treat this like a probability question and I show my work, I don't have to think about it like a different special distribution. Okay, and again, on geometric problems, you can do that. Okay, you really can. First success has to happen on roll number 3. So there's roll number 1. There's roll number 2. There is roll number 3. Okay? If I showed that work with my answer of 0.116, I don't have to get into any of this geometric stuff. Okay? Fail, fail, success. Okay? That's probably a question I could not even have mentioned anything about a geometric distribution, and you would have said, well, yeah, I mean, if I know the rolls are independent, I can just use rules of probability, and I can figure out that it's 0.116. And that's the way I want you to approach these kinds of problems. Okay? What is the probability that it takes more than 3? That x will be at least 4. Okay? This one might stretch you mentally a little more, but again, I can just use probability rules to calculate what this is. Okay? This one isn't saying it has to happen on the fourth roll. It's just saying it has to happen on the fourth or after. Now to do this, there's basically one scenario I need to play out. I need failure on the first, failure on the second, failure on the third. And that's it. That's all this problem is really saying. If I'm going to get my doubles on the fourth roll or after, that's what needs to play out. I need to not get doubles on the first three. Okay? Now for the interpretation, this would say that there is a 57% chance it will take more than 3 rolls to get doubles. Right? 57% chance it'll take more than 3 rolls to get doubles. Okay? The geometric stuff is there in your notes packet if you want to look at it again. But the only thing I want you to recognize there is if it mentions like when the first success occurs, don't treat it like a binomial. Okay? Because it's not. Just use your probability rules and take that approach.